And now it's time for the latest exciting episode of Doz's Television Workshop.
Hello and welcome back to Doz's Television Workshop, where today I'm going to be having a look at this AM experimental transmitter kit that I bought from AliExpress. I actually bought this one assembled, but I'd just like to talk you through it and explain some of its shortcomings, and yeah, let's attempt to put some of those right. Comes with actually not a bad set of instructions, and it's sort of a bit educational, really. Objective: understand the principle of high frequency signal oscillation of AM transmitter. Understand the principle of high frequency signal amplification of AM transmitter, and understand the modulation principle. And it's not a bad document. We have to read through some of the interesting translations at some pace. It's in Chinese for a lot of it. Let's just skip through here, and then we've got a translation. Comes with a schematic. Some diagrams have obviously been plagiarized from the web somewhere, but yeah, instructions in English, and yeah, it's pretty good, except for a few things. I'll just take you through the schematic quickly. This is the schematic. It's pretty accurate. I have tested this already. They reckon its output, by the way, is about 400 milliwatts at 9 volts. I didn't get anywhere near out of it. I must be honest. You're probably good for about 200 milliwatts, really. Anything other than that, and the modulator sort of falls over and it all gets distorted and horrible. But I'll show you how it works. This here is just an oscillator, and it's based upon this polyvaricon capacitor here and this coil here, which we can see there. And this is one of its shortcomings, actually. This coil adjusts the sort of low end, which they say it's set for 530 kilohertz, and this sort of adjusts the frequency in the top end of it. That's one of its major shortfalls in my book. It is so touchy to hold it on channel. You just have to breathe on this thing and you're on the neighbouring channel. I mean, it works, but it's not very thermally stable. Yeah, it sort of drifts as it warms up, and not very good. It's one of the things we need to address on this. So there's our oscillator transmitter. Here's our L and C here. The L is just a stacked inductor there. That comes out, feeds a driver transistor, which drives this one-to-one transformer, which is actually this green ferrite there. That's the RF, then comes out of there. We've got a biasing control here, SW2. That's the other problem with it. They've put all the parts values on the board, but none of the SW, the identifiers. But I happen to know that is that pot there, and that biases Q4. There's a protection diode in there. They've thought about this. Protection diode, and there's a 2SD882, which is our RF output transistor, which is this one mounted just vertically on the board there. It's then a bit of DC blocking, and then there's a very nice filter here. On testing, as long as you're above sort of 1 megahertz, it will go down to 530, in which case you will see a second harmonic. But if you're above sort of 1 megahertz, this does very well. And that's formed by these two coils here and these ceramic caps down here. So we have some adjustability in the output filter there. J3 is the antenna connection. It's written in Chinese, can't remember which one is which. And the other one is ground, that's for your antenna. Now, yeah, modulator. So this is another one of its shortcomings, which is quite easily addressed, really. So the audio comes in via a 3.5mm jack, this one here. It's combined to make mono, because it's a mono transmitter, obviously, being AM. No AM stereo here. There's a level control, which is actually this bizarre looking pot here. So that is our modulation level there. Feeds a CD7368 or a TA7368 amplifier, which is this sill component here, running along the bottom there. It's just an audio power amplifier. Not a lot of power behind it. There's a red LED hanging off the supply rail, just to tell you it's on. So yeah, that is just supplying audio. So yeah, that enters that point A, which then comes up here, A. It's DC blocked. And then we have a pot here, which is our modulation depth pot, which is actually this skeletal thing over here. Audio comes up here. Now this sets a bias point here. They put a second cap in there, which I think is rather tricky. You don't really need it, but it stops current flowing back down this pot and making it scratchy. So actually you probably do need it, but I've seen plenty of people get away without it. So yeah, they've thought about this. This SW3 pot here, actually that one there, controls the bias of the modulation transistor. And you sort of want to pitch that, is when the thing's idling with no audio going in, you want to pitch that so you've got about half rail on the output of the circuit just before L1, which is here. But you can twiddle that about, and it is quite tolerant as to where you set it, and it does vary a bit with the loading on the antenna. Maybe we'll look at that, maybe we won't. But that then supplies via L1, which is an RF choke, dirty great big coil there, L1, to our RF output transistor. So you've got a bit of audio coming in here, and effectively, if you imagine this as a voltage regulator, and it's just being controlled by the audio, so the voltage that the thing is managing to regulate is going up and down with the audio, so it supplies audio as power to the output transistor and then modulates our RF, and we get AM. Really is quite clever. So that's how it works. Now, the shortcomings I wish to address are the oscillator, because it drifts like mad, and the modulator transistor itself, and that's where I'm going to start, is with the modulation transistor, because this is just silliness. Here is the modulation transistor. You can see they've thoughtfully mounted it on a heatsink there, but yeah, spot the problem. Let us zoom in. That's the wrong way. So you can see they've bolted the transistor upside down. I reckon it was a board layout error, and the transistor should have been the other way up, or maybe attached to the other side of the board, maybe, and then we're just going to use, I see they've put a large chunk of copper there, maybe to act as a heat sink. I'm not sure, but yeah, they've bolted the transistor with the thermal pad pointing upwards. It's not doing much really, is it? So what I'm going to do is I'm just going to take that nut off there, if I can. Maybe a little bit of a screwing action going on. Maybe a bit of screwing and plier action going on. And we're just going to turn that heatsink up the right way. Zoom out again. There we are. Oh. I have to say, when you start powering the thing up, this modulator transistor does get a bit warm. It's doing quite a bit of work. So let's just take that out of there. Right, and then we're going to just reverse it so it sits on the top. Should we have a bit of therm path in there? Can't see why we wouldn't. Let's give it every chance, shall we? Not that the heatsink's all that massive, but let's make it happier. Oh, I've managed to get it on myself already. Oh well, in for a penny, in for a pound. Let's just smear that on there. Lovely. So, now I've got the problem, is how am I going to bolt is that bolt going to be long enough to go all the way through? Here's hoping. There we go. That should improve that no end. Right, now to deal with the frequency instability. Right, one thing I do need to mention before I carry on is precautions for use down here. I'm quite surprised to see this in this, to be honest. When using the micropower transmitter, avoid the local radio station. Do not affect others listening to the radio and abide by local management regulations. This machine is only for radio enthusiasts to experiment and test old medium wave radios and cannot be used for other purposes. When transmission distance exceeds 5 meters, the power supply voltage can be reduced to reduce the transmission power, and the transmission antenna can also be shortened to reduce transmission power. Now, in the United Kingdom, this isn't within the realms of the law at all. Whilst you can purchase one of those little FM sort of Bluetooth adapters, I use one in my Mini to make a very local radio station, if you like, on FM. I use it for connecting my Bluetooth to my old radio in my classic Mini. That's perfectly legal. In the US, you can do this on the AM band, up to, I think, 100 milliwatts of radiated power. Check that. I am not sure. I am not in the US. It's called Part 15, and you're quite legally allowed to do so. In the UK, you're not. Thou shalt not transmit on medium wave. Of course, medium wave is being abandoned left, right and centre all over the world. Certainly in the UK, there is plenty of space to be playing with, but technically this is not legal. You are, if you connected this, to a substantial antenna system, you could indeed incur the wrath of Ofcom. It's probably best not to do that because the fines could be heavy, especially if you're transmitting music on here as well. You're in breach of PRS and all manner of licensing to license the music. So yeah, that's not good. So yeah, just bear in mind this isn't legal. All I want to do is generate a signal that will not leave the walls of this house, so I can just test my radios. If Ofcom are watching, I'm probably breaking the law, but I think, be sensible with this. Don't try and broadcast to your neighbourhood with it. That would be bad. Right, let's look at that frequency stability. Right, so frequency stability, how are we going to address this? There is a chap in Scotland, I believe, Scottish gentleman anyway, called Murphy310 on YouTube, and he's added a crystal into this circuit, which will lock the oscillator to the frequency of that crystal. Got problems with that. One, we don't have a crystal, and that means getting something made. So we'd have to have a crystal cut for our frequency. In this case, I think I want to be on 1593 kilohertz. So yeah, I'd have to go out and have a crystal cut for that frequency, which can be quite expensive. There used to be a company called Quartz Lab here in the UK that used to do crystals cut to specifications. But if you want something a bit special, it's going to be money. I suspect there are Chinese crystal manufacturers that would do that for you. But again, it's going to be some money. The other problem with it is you are then fixed to that one channel. You can't move about. Say that channel got noisy for whatever reason, or you wanted to try a radio on a different frequency, you can't alter that. So it wouldn't be frequency agile, it would be fixed frequency. And whilst I suppose that may not be much of a problem, it's something we could deal with, I think. So my plan is to use this. This is a frequency synthesizer board. It is tiny, banana for scale, and it contains an AD9833 frequency synthesizer chip These are not expensive, available on eBay, etc., AliExpress. Yeah, so that is a little module we can use. It is, of course, controlled by a microcontroller, so I'm going to choose an Arduino Nano, although later on in the project I may change that. In fact, I probably will change it, but this will do fine to get us started. Right, let's make something up, probably on a breadboard will be good enough to start with. Right, well, after wiring up a few bits and pieces and having a little tinker about with some code, we've got a sine wave output. We should have a sine wave output. There it is. So yeah, there you go. We have got 1593 megahertz, or 1.593 megahertz, 1593 kilohertz. It's a sine wave. The only thing I'm worried about is it's only got amplitude of about 600 millivolts peak to peak. So I think what I need to do is actually have a little look at the output from our oscillator. But if we just head over to the computer, I'll just show you the code. If I just go into Library Manager, I'll show you the library I used. AD9833. It was this top one here by Rod Tillart. I think we've used his libraries before, haven't we? But it's, yeah, ever so straightforward. Creates the object. Pin 10, by the way, is stipulated here. That's your chip select pin, which goes to the function pin on, or FS select pin on the chip or module itself. SPI begin, analog devices begin, then set frequency, and as you can see it here, I've set for 1593, channel 0. We want a sine wave output, and yeah, it actually just prints out the serial interface. The frequency it's set, we don't need that line really, but yeah, there you go. The one thing I will say, that if you set it to square wave, you do get a 5 volt peak to peak output from it, which would give us loads of drive, but it's square wave, and then we'll have to filter out the harmonics probably, although there is a low pass filter on the output of our transmitter. It's yeah, let's not give it too much to do. So yeah, what I'm going to do next is if we refer back to the diagram here, I shall zoom in post. What I'm going to do is I'm just going to measure the output on this C20 here on the oscillator side of it. I expect there to be a bit of a DC offset there, but let's just have a look at the output amplitude and see if our driver circuit is going to give us enough oomph to drive this transistor as if the oscillator was running, but accurately. Right, let's measure that. Okay, I've got the transmitter connected up. This is the power supply. We've got 9 volts. We're consuming about 400 milliamps, just under, and I can confirm that this 51 ohm resistor I've got across the output terminals here, yeah, it's that's warm. So okay, so what we want to do is scope up on the input of that capacitor and see what sort of output we're getting there. So we're getting nothing. What's going on here? There we go. So there is our, what are we at? We're about 1.2 megahertz, just about. But that's the output from our oscillator. The important thing to notice there is the fact that that is about 7.6 volts. So we've got a long way to come up from our 0.6 of a volt from our oscillator. So let's set about building an amplifier for it. So I've been playing around for a couple of 3 hours, and yeah, developed a little amplifier with a 2N2222. Worked very nicely. From a 9 volt rail, we were swinging 6.7 volts, little 2-stage buffer amp. and connected it up, and it was all right, worked. And then I got to looking at the schematic again, and I'm thinking, if I just take off C471, which feeds the base of our oscillator buffer transistor with the transformer in it, surely with 600 millivolts on there, I should be able to swing enough current into the base of the buffer transistor to do the job. And I thought, you know what, I'm going to try it. And if you glance over there at the oscilloscope, that's our output waveform. I have to say it's very good. I'm very pleased with that. So yeah, all that unnecessary sitting down, scratching my head, making a buffer amplifier, absolutely unnecessary. All we've got to do is move current into this base, which our DDS is quite capable of doing. It's actually got a 50 ohm output. So yeah, it can move enough current in there. The only thing I will say is SW2, which is this 200 ohm pot over here, needs to be almost minimum to get the right amount of RF coming out of it. So yeah, the driver transistor is now running quite cool. The modulator transistor, the one we reverse the heatsink on, so that's good. So if we just try and modulate it slightly, this is a YouTube track. I'm just going to change that actually, because I want to demonstrate something else as well. Yeah, this is the right track. So this is just a radio tuned to the prerequisite channel. And there you go, modulating quite nicely. If I turn the scope down, actually, you'll be able to see the modulation there. So that's working quite nicely, but the one thing we're lacking there is much in the way of compression, and also that track is bandwidth unlimited. Now, back in the day, I think Ofcom used to say you could have 6 kilohertz of audio modulating your AM signal, which would actually give you a band of 12 kilohertz. But the medium wave channels are only 9, so maybe some of them with the higher power stuff was limited to 4.5 kilohertz. I've no idea. But you can hear this, it's getting slightly distorted. And that's because the filters in my radio probably only about 9 kilohertz wide anyway. So what I've done is I've made another version of the same track. It's a YouTube library track, by the way. Yeah, this is the one. And what I've done is I've band limited it to more suit our broadcast technology, if you like. So this is cut off at the low end about 150 hertz, and I've cut it off at about 6 kilohertz on the other end. And I've added some compression as well. Did all that in software. And as you can see, it's got much more punch to it. Nice. So our new frequency synthesizer working well. All I want to do now is add an audio compressor onto the front end. Yeah, I'm going to try and do that in software. Let's have a go at it. One thing I will just mention before we get on with that is I have removed this polyvaricon because I was trying to see if I could reutilize this transistor at the start here to be part of my buffer amplifier, which I could have done, but yeah, it wasn't needed in the end. It's not needed at all, and that's working perfectly. By the way, I did a little calculation and I reckon we've got 300 milliwatts out. So they reckon 400, but I never really saw that when it was just in its standard form. So yeah, quite pleased with that. Right, I've decided to go a bit unconventional with this. Now, back in the day, we'd have achieved some filtering and a little bit of compression using a bucket of op amps and even sometimes light dependent resistors and light bulbs to do this sort of thing. I I'm going to bring this kicking and screaming firmly into the 2020s by using this. This is a Teensy 4.1 microcontroller. I think you could also use a Teensy 4. It's just the fact that we happen to use these at work. So I am well versed in their operation. So I bought myself one. And we can't just throw audio into that and fiddle about with it. Now, the microprocessor on here, the microcontroller, is a Core M7, and it's running at 600 megahertz. It's got plenty of space, plenty of speed. So I'm hoping we can do this. Now, to get audio in and out of it, I've purchased this. This arrived really quickly, actually. I bought this from Pimeroni, and this is the Audio Shield. Specifically designed for Teensy. So what happens is, if you've got a Teensy 4, it just fits straight on there, or a Teensy 3 point something. I think they do a version for it as well, although I don't think they're available anymore. But it sort of straddles that micro like that, and we can just solder that on there. You do need to make sure you've got enough clearance between all the bits. If anything hits in there, we could be in trouble. I will check for clearance. No, we're good. So I can just solder that on the bottom of there. Now that gives us what's known as an I2S audio interface. Now an I2S is a very fast I2C type protocol that's just designed to handle CD quality audio. Clearly our AM isn't CD quality nor even stereo, so we haven't got to worry about stressing it out too much. But the Core M7 has sort of inbuilt DSP functions, so we can apply those to our signals going in and hopefully create a filter and a bit of compression. Let's see how we get on. Right, well, I've had a very pleasant afternoon and evening coding and a steep learning curve, and I have created this thing. So just to give you some idea of what's going on, audio is coming in from my dear old MP3 player. It is feeding the Teensy Audio Shield here. It comes out of the Teensy Audio Shield back into this Tascam recorder here, so you can hear the sound directly, and then back off into my workshop amplifier. So let's just go and have a look at the computer and see what I've done. Okay, so this is the Teensy Audio System Design Tool specifically for the audio library. As you can see here, we've got SGTL 5000, which defines the chip that's on the audio shield. Our analog audio comes into that shield, gets turned into I2S, which is here on this input here. You can see we've only got one channel because we're only mono. That feeds a peak detector here. I shall come back to that one in a minute. It also feeds this amplifier here. Now this amplifier is normally in attenuation, and I shall tell you why in a second. So that feeds this peak detector here. Now this peak detector listens to the output from this amplifier and keeps it below a certain level. It's got quite a slow attack and decay on it, so it's more of an automatic level control than anything, and that prevents us overloading this filter here. Now this is a biquad filter, and what that's doing is our band pass. So yep, that then feeds yet another amplifier with a peak detector. Again, this is another quite sluggish AGC, which is then feeding this multi-band filter here. So we've got low pass, high band pass and high pass. I'm not sure which order they're in actually, but they feed another 3 peak detectors, which these 3 peak detectors control the levels applied to this mixer, and this gives us a kind of crude multi-band compressor. That then output falls out of there back into I2S, where it's turned back into audio. This peak indicator here, which is the first one in, is just there to provide a clipping indicator on the Teensy itself. So if we fire over to the code here, I wrote 2 versions. This is quite a simple version. See how short this code is. This is just a quite basic filter and compressor. And I built on this to add the more functionality in. This tends to be a bit harsh and a bit sort of pumpy, which I wasn't keen on. So then I moved over to this. Again, very similar bit of code at the start here. This code, by the way, is generated by this when you click export. And there's the code, and you simply cut and paste it into your Arduino sketch. And yeah, that's that bit there. So yeah, we've got some variables here. This defines some peaks, the maximum we can allow. This is to prevent clipping in the chain. We've got our low pass currently set at 6 kilohertz, our high pass set at 100 hertz. We've got some other floats that are setting various limits here. There's a rate there as well, which defines the rate at which the compressor, the attenuation, can move. There's some setup there. Yeah, and these are the individual peak detectors and sort of limiters, if you like. And because we've got a bunch of them in sort of series, it does make it it's quite subtle, and I'm quite pleased with it. So just to give you a demo of that, let's move back over to here. Now I've got, as I said, this MP3 player feeding via the compressor and the filter via our DSP back into here, so you should be able to hear it directly. Let me bring up a tune you may all be familiar with, and yeah, take a listen to this.
But tales of yesterday, does his magic fingers make them work and stay? Crack screens turn new, pixel by pixel, micro-soldering the pathways with hands so nimble. History of the radio, waves is in his eyes, a dance of electrons under neon skies. Bring back color in the dark. Screens that buzz, it's magic on display. Old TVs revived in a brand new way. Circuit woes, but we're getting closer. Neon signs, they guide you to the door. Tubes and screens like you've never seen before. Pulses hum, sparks begin to fly. In this tiny shop, dreams are set too high. In Darcy's shop, with a touch of love, your picture's clear and true. In Darcy's hands, pixels flicker back to life and stand. Microchips and vintage heart in a world of screens playing their parts. Circuit boards with stories to untangle. Every wire a promise at an angle. He bends the light through the lens, creating onyx nights. Oscillators, creating sonic waves, bringing back the charm of retro days. Capacitors and resistors. In Darcy's touch, there's no misfire. Transistors dance to the rhythm of repair. Through the glow, feels like magic fills the air. Voltage pulses to tune's melodic run. A symphony of sparks where the work is never done. In Darcy's shop,
So there you go. I'm going to do that again, but with that first compressor loaded up, which is a little more punchy, and I'm not quite so sure on it.
But tales of yesterday, does his magic fingers make them work and stay? Crack screens turn new, pixel by pixel, micro-soldering the pathways with hands so nimble. History of the radio, waves is in his eyes, a dance of electrons under neon skies. And spark, fix the picture, bring back color in the dark. Screens that buzz, it's magic on display. Old TVs revived in a brand new way. Circuit woes, but we're getting closer. Neon signs, they guide you to the door. Tubes and screens like you've never seen before. Pulses hum as sparks begin to fly. In this tiny shop, dreams are set too high. In Darcy shop, with a touch of love, your picture's clear and true. In Darcy's hands, pixels flicker, back to life and stand. Microchips and vintage heart in a world of screens, playing their parts. Circuit boards with stories to untangle. Every wire a promise at an angle. As he bends the light through the lens, creating onyx nights. Oscillators, creating sonic waves, bringing back the charm of retro days. Capacitors and resistors, in Darcy's touch, there's no misfire. Transistors dance to the rhythm of repair. Through the glow, feels like magic fills the air. Voltage pulses, a tune's melodic run, a symphony of sparks where the work is never done. In Darcy shop, with steady hands.
Yes, with steady hands, no less. So those are the two compressors. That second one, a bit harsh. I shall make both of them available on my GitHub. The harsher one's just called Teensy AM Processor. The one I prefer, I think, is called AM Processor Multi, but I shall make those available in links in the description down below. So yeah, there we have it. It's a fascinating thing to want to play with. Please do have a go at the code yourself, because I am sure there are many of you that are better at coding than I am. All I did really was listen to it and keep making changes until I sort of became happy with it. The other thing I just wanted to show actually is how it copes with spoken word, because I always think that's a quite good judge of a compressor. Let me just load up the multi again. And just push that to the teensy. And I thought about some spoken word and where was I going to get that from, and I thought, Radio 4, but let's face it, I take dire liberties with the BBC as is. So yeah, let's go into my own YouTube channel. Now the problem is I do compress the YouTube slightly in post, I'm going to avoid doing that for that audio, by the way. I'm going to leave that audio as it is. YouTube will probably mess it up anyway, or at least have a go at it, because they do that. But yeah, let us just bring up one of my videos. Where's one you'll have seen recently? There we go. So yeah, let's just have a listen through that. So I've got the multi-band compressor lined up again. Let's just press play on that and see how this comes out. Oh, we've got an advert. Hello and welcome back to Doz's Television Workshop, where today we're going to be taking a look at this Auric 1 computer that I bought from eBay. Let's get into it. So here it is, the humble Auric 1. This purports to be a 48K model, and yeah, this is the computer I sort of first had as a kid. I must have been, I don't know, 13 years old, something like that, 12, 13 years old. Yeah, there you go. Sort of gives you an idea of how it copes with spoken word. I have to say my audio is always, when I do the hello, it's Doz's Television Workshop, I always manage to overload the recorder. There we go. Anyway, that is working really well. So I think I'm passing that as fit. Now I'm just going to go back to our frequency generation. Right, well, it's a few days later and I have evolved the frequency synthesizer somewhat. We now have a set of dip switches along here, which allows us to select every medium wave channel. So dip switch 1, for example, just one on its own up, will give us 531 kilohertz in Europe, all the way up to 1611. I don't think 1611's used anywhere. It used to be Vatican Radio years ago, but I think that's gone now. So yeah, we can select our channel here. Now, I did think about those people across the pond that may be watching. We do have quite a few viewers in the States. So if you select bit 8, it becomes 530 kilohertz, because Americans use 10 kilohertz channel spacing between 530 and 1711. Interestingly, they end up with fewer channels. But there you go. So yeah, bit 8 will select 10 kilohertz spacing. Down is for 9 kilohertz spacing. So yeah, I will leave a link in the description below, because I'm actually going to write this up on the website, and I shall publish a chart there of all the channels, so you can pick the one you want. The other thing I want to know, to just show you briefly, is calibration. There's a rather easy way to do this. Now, in my locality, I just want to select 693 kilohertz, which is 11001, and all the rest are zeros. 11001. Get that right. So it's bit 5 on. 6, 7, and 8, 0. I've also put a power supply on here now as a little 7805. The other thing I did change was I've changed the power supply for the 9833 module from 5 volts down to 3.3. Because my understanding is the oscillator on there is actually only rated to 3.3 volts. They don't tell you that anywhere. They just tell you this module's fine on 5 volts. Might be for a little while. Anyway, the reason I've selected 693 is that's where BBC Radio 5 live broadcasts. So if I just switch my radio on. There we go, that is 693. I've added a variable into the program for the Arduino called fcal at the top, which allows us to alter the frequency calibration. I have deliberately miscalibrated this one. Let's just switch the oscilloscope on so you can have a look. Right, so that is 693. I'm going to turn the volume up. And I'm going to plug our synthesizer in. There you go. You can hear that tone. And that's because our oscillator is off frequency with the BBC on 693, and they should be pretty accurate. So we're creating a heterodyne in between our oscillator, just with the radio near enough to it, and the BBC. So if we can tune our oscillator so that heterodyne is minimal, then we should be pretty much on frequency. So I'm just going to alter my frequency now on the computer. So one moment, please. And I'm just going to take that down to there. The free FCal value, by the way, can be positive or negative. I've tested a couple of these modules and they do vary a little bit. I am just programming the module now. There we go, uploading. So there you go. Now you can hear it fluttering very quickly, which means we're getting closer to our frequency. I happen to know this one seems to be about too low, 2 hertz. So I've just moved it down to 2 hertz. So let's see what happens now.
Climbing the table yet again. Second they will be.
There you go.
And as we said earlier, guaranteed.
It's very, very slow now, and it's less than 1 hertz. And to be honest, we can't do much better than that. What does the scope say we're doing? 692.999 hertz here on the bottom of the display. To be honest, I'm not quite sure how good the frequency counter is in that scope. I've questioned its accuracy before, but here we are. We are a fraction of a hertz away from the BBC on 693. So, 693 kilohertz. Any radio station you can do that with that's local to you. Don't do it at night if there's fading going on anyway. You're receiving a distant station and it's fading in and out, because you might mistake that for you know, the heterodyning itself. But that's a simple and easy way just to calibrate our frequency output there. Right. One other thing. Because this has been quite successful, I'm quite pleased with that. I've implemented it into our Teensy audio processor as well. Exactly the same MO. I've got to finish the power supply yet, but I just thought, well, there seems to be little point in you know, using 2 microcontrollers if I'm going to build it all into one little pantry transmitter anyway. So what I've done is I've just duplicated the circuitry. The sketch and libraries are a little bit different, but I'll publish both of those on my GitHub and leave links in the description below. Right, I think it's time to sort of want to put it all together. Let's get on with it. It's Future Editing Dos here, and once again this video has gone on for far too long, so we're going to leave the assembly of the transmitter until next week. Until then, click like, subscribe, do all that rubbish, and I'll see you really soon here on Doz's Television Workshop. Cheers now, bye.
With a gentle hand, he brings them back in line. Every twist and turn makes the magic shine. Cathodes and the crackle of the tubes amidst the dust. They play nostalgic tunes. Solder smoke and the faint aroma of time in each repair. An art that's so prime. Where wires twist and spark, fix the picture, bring back color in the dark. Screens that buzz, it's magic on display. Old TVs revived in a brand new way. Circuit woes, but we're getting closer. Neon signs, they guide you to the door. Tubes and screens like you've never seen before. Pulses hum as sparks begin to fly. In this tiny shop, dreams are set too high. With a touch of love, your picture's clear and true. In Doz's hands, pixels flicker back to life and stand. Microchips and vintage heart in a world of screens playing their parts. Circuit boards with stories to untangle. Every wire a promise as an angle. As he bends the light through the lens, creating onyx nights. Oscillators creating sonic waves, bringing back the charm of retro days. Capacitors and resistors. In Dazzy's touch, there's no misfire. Transistors dance to the rhythm of repair. Through the glow, feels like magic fills the air. Voltage pulses, the tune's melodic run. A symphony of sparks where the work is never done.